Our last section of projectile and circular motion will be covered today, and we'll come back to a few of the concepts that we talked about on the first day. So circular motion. Circular motion can be kind of tricky. The key is that you have to believe in Newton's first law of motion. Let's remember what that is. The first law says that an object in motion in a straight line at a constant speed remains in motion in a straight line at a constant speed unless acted upon by an unbalanced force. So, since things that are moving in a circle are not moving in a straight line, based on Newton's first law, there has to be an unbalanced force on them to move them out of that straight line path. So that's the basic idea here. Let's see. Nothing can turn or change its direction unless there's a net force that causes a change in the motion, and that net force is always perpendicular to the turn in the object's motion. Let's think a little bit about a softball on a rope. So you can stop this for a moment and grab the softball on a rope and someone swing it over their head. And let's think a little bit about what happens that keeps the ball moving in a circle. So go ahead and stop this, pause it, and then come back. Okay, so now you're back. Let's think about the ball that's moving in a circle. Pretend there's a rope on it. I couldn't get a rope to show up on the screen. So there's a rope on this ball, and the rope keeps the ball moving in a circular path. If the rope weren't there, then the ball would move in a straight line at a constant speed. But the rope keeps the ball moving in a circular path. Now, we missed one. Let's go back to, now let's think about Newton's cannon. If you remember that from the beginning of the unit, Newton's cannon is a situation where objects, it was imagined by Newton that if he could put a cannon on the earth and shoot a cannonball at just the right speed, it would just fall around the earth continuously. And that's precisely what satellites do. So let's look at this. This is the orientation of the velocity and the acceleration for an object moving in a circular path. So we have a blue ball going around in a circle, and v sub t on this screen is the tangential velocity. So that's the velocity along the circular path. A sub c is called centripetal acceleration, and the tangential velocity and the centripetal acceleration are always at right angles to each other. The tangential velocity is tangent to the curve, so that's pretty self-explanatory. The centripetal acceleration always points toward the center of rotation, and the force keeping the ball moving in a circular path is called the centripetal force, and we find it by taking the mass of the object times the centripetal acceleration. And that centripetal force always points toward the center of rotation as well, because remember that forces are in the net force is in the direction of the acceleration. So it shouldn't come as any surprise that the centripetal force and the centripetal acceleration both point in the same direction. They have to. And these are all very testable concepts, particularly the orientation of the centripetal force to the tangential velocity and the direction that the centripetal force and the centripetal acceleration point. Very testable ideas. So again, turning, curving, anything other than a linear motion is always caused by an inward force or a centripetal force. Centripetal means center seeking. I've got centripetal or centrifugal here on the screen in red. I want you to not think about that. Never, never, never use centrifugal. It's a centripetal force. center-seeking force. So the forces that keep things moving in a circle are called centripetal forces. Okay, so what happens if those centripetal forces disappear? Okay, the first law says that objects will move in a straight line unless a net force changes their path. So, if you have something moving in a circle and suddenly there isn't anything to keep it in a circle any longer, according to the first law, it should do something quite predictable. Let's look at this picture. This is like a picture of the ball that we were spinning at the beginning of class. And the centripetal acceleration here is pointed toward the person who was spinning the ball. And the tangential velocity is along the path and perpendicular to the centripetal acceleration. So if this rope suddenly breaks, then this rock would move in a straight line because there's nothing keeping it in a curve any longer. Let's look at it from above. So if the rope breaks, there it goes. It goes in a straight line. So when something is moving in a circle and the force keeping it in a circle disappears, or the centripetal force disappears, or the centripetal acceleration disappears, in this case the rope, if the rope breaks, then the ball moves in a straight line tangent to the circular path at the point that it was whenever the string broke. Look at this ball on a platform dolly and think about it. Think about the same idea here. Now remember that this is going to be a little bit different because in this case, what you're seeing right here on the left is that the ball is continuing in a straight line and the platform is curving. So there is a motor or a driver of some sort on the platform, and it is applying a force only to the platform and changing the direction of the platform, but not changing the direction of the ball. So the ball continues in a straight line. On this side, on the right, the same thing is happening. There's nothing keeping the ball on the platform, except that whenever this one turns, there is a little wall here, so the ball can't roll off. The ball instead rolls into and stays attached to the little wall that keeps it from moving. So that's kind of interesting. So keep looking at this and think about that idea. The ball on this side is definitely showing Newton's first law. It's continuing in a straight line at constant speed. This one would do the same thing, but it's prevented from continuing in a straight line because it strikes the little wall on the platform. Okay, so in review, circular motion is always accelerated motion, even if the speed around the circle is constant. The reason it's accelerated motion, even if the speed stays the same, is because the direction is changing all the time. So circular motion is always accelerated motion. Circular motion requires a centripetal force that points toward the center of rotation, and circular motion is always accelerating toward the center of rotation, and the centripetal acceleration is pointing toward the center of rotation. Those are all very testable ideas, very testable concepts. Well, thank you very much, and I will see you soon.